Okay. All right, everyone, we're going to get started. Welcome to WACV 2022. Woo, we are actually here in Hawaii. We made this happen. I want to note this is the first meeting that is co-sponsored by the IEEE Computer Society and the Computer Vision Foundation that has been held in person since WACV 2020 in Aspen. If you were there, you may remember that was the week the country started to shut down. We had hoped it would be a temporary problem, but here we are. That said, the organizers of this meeting have done a fantastic job making this happen so that it's hybrid. We have a bunch of us, right, who are here in Hawaii, but we also have a lot more folks out there in the Zoom. So don't worry about the Zoomers, try to interact with them if you can during this meeting, and we'll hope to convey as much information as possible to them through the magic of the internet. So aloha and welcome to WACV. I want to acknowledge our corporate sponsors for this meeting who are very gracious in giving some funding to the meeting and who are out there recruiting in some cases, so talk to them if you see them. We have Amazon, Google, Kitware, MITRE, and Verisk. I want to say a few words now about the organizing team itself and the tremendous effort they put into organizing this meeting. First and foremost, the most important person, the key person who made this happen, Nicole Finn, who is out there at the registration desk from C2C events, just put in a heroic effort to make this happen up to the very last minute, ensuring everything would be safe, would be running on time, getting all of the pieces put together. So we definitely owe her a huge round of applause, which we hopefully can hear out there. Of course, as usual, we have a cast of characters who've done a great job putting the program together, different elements of the program. Our workshop chairs, Vito Strush, who is here, and Margaret Betka. Tutorials, we had Philippos Mordechai, Doctoral Consortium, Nathan Jacobs, just phenomenal across the board. Some of these events will be happening too as this meeting proceeds, right? We've got more workshops on Saturday. The DC is tomorrow. Finance chairs, Ginger and Terry Bolt, who always do a phenomenal job. Terry's over here in the corner. Publication chair was Eric Mortensen, who is a key person in our community who helps out tremendously with all of these meetings, not just WACV, but also CVPR and ICCV. He's also here. And our diversity, equity, and inclusion chair, Georgia, who did a phenomenal job putting together our plan for that. Program chairs, right? The folks who did an enormous amount of work to put this program together. As all of us know, WACV is growing in popularity and importance. It's now an open access proceedings, right? So there's tremendous attention put on it. And so we're getting more papers. And so we had to put together a fantastic team of people to handle all of that. Ryan Farrell was our lead program chair. And this is the fourth time in a row you've done this, is that right? Three, okay, almost. We were close. The three is pretty heroic, but this is really excellent. Ryan really led the process and trained up some new folks, which is good, right? Getting more people involved from the community to be able to vet these papers, get this process rolling. It's not a trivial task these days to do a review cycle for any conference in computer vision. Joining him was Catherine Zhao, Saket Anand, and Richard Souvenir. All did a phenomenal job putting this program together. And then, of course, the general chairs who stood by and supervised everything. Gerard Midioni, who is next to me, Kevin Boyer, who is next to Gerard, and of course, I'm Walter. We definitely, again, wanted to make this happen in person in some capacity, and we did it, so cheers to us. We've got a great lineup of keynote speakers here. We've got Kristen Grauman, who is speaking today, I believe. We have Ahmed Elgamal, who's speaking, and Zhenyu Zhang will also be speaking. They have great things to tell us about what's happening in terms of the intersection between academic research and industrial research in particular, right? WACV has always had this flavor of applied research, and all these folks are doing tremendous work, so I'm excited to hear what they have to say. A little bit about the meeting. Again, that we were pretty nervous because this was going to be, a meeting with an in-person component. We didn't know how many papers we would get, how many people would actually show up. But we had quite a bit of activity here. 305 first-round submissions, 859 second round submissions, tremendous numbers. 1,104 of these were fully reviewed. There were some desk rejections. And again, all these numbers look good compared to previous years. Again, we know there's a lot of uncertainty right now with the pandemic. And then 35% of the papers were accepted, so we've got 406 papers appearing in our proceedings. And what's great to see here, we have 786 registered attendees out there. Phenomenal. 317 of us are here on the Big Island, so that's great. Okay, I'm going to turn things over now to Ryan. He's going to say a little bit more about the program.
Thanks, Walter. One thing I forgot to add at the last minute. We had 406 papers accepted. 123 of those we're expecting to present here. And many of you will be doing that. We're grateful to have you here. Really excited to hear from you. We had 88 area chairs. Want to thank all of them, along with, I think, approximately 1,200 reviewers. And really, we could not put on the program without your efforts. So thank you to everybody who was involved there. So to start the conference today, we're going to have the award session. Okay, there are four. We'll get to that in a second. We're going to have one of those live and three of them remotely. I first want to thank our awards committee. We had a committee of 5 outstanding individuals in the community who formed a committee, and Larry Davis, Yana Kosika, Greg Morey, Tanvir Sayed Mahmood, and John Boshi. And we provided, through area chair and reviewer nominations, 17 papers, and the committee selected 4 award papers. The 4 awards were for the best student paper, best paper honorable mention, best paper in algorithms track, and best paper in the applications track. Again, as Walter mentioned, WACV has both an algorithms, or sort of more theoretical side, and an applied focus as well. So we give separate 2 best papers there. So, drum roll, we're going to go ahead and we'll let you know who the 4 are, and then we're going to hear from them each after this. The best student paper goes to Agree to Disagree, when deep learning models with identical architectures produce distinct explanations. And the authors are Matthew Watson, who will be presenting the paper via Zoom, Bashar Awad Sheikh Hassan, and Nora Al-Mubayed. Give them a round of applause. And so for each of these award papers, you'll see down in the bottom left what session it's going to be presented at. So tomorrow, first thing in the afternoon, in the 4B session, this one will be, it's not going to be live. I think Matthew's remote because of the last minute couldn't make it, but he was scheduled for that session. So, okay, the best paper honorable mention goes to Strumming to the Beat, Audio Conditioned Contrastive Video Textures. Authors are Medini Narasimhan, Shiri Jinisar, Andrew Owens, Alexi Efros, and Trevor Darrell. Let's give them a round of applause. And so Medini will, I guess with all of these, you're going to hear their slightly longer talk in the award session, but that one's scheduled for later this afternoon. And then this one, you'll be able to meet with Medini at the poster session time if you have further questions, okay? Best paper algorithms goes to Whole Robust Wireframe Detection by Nejin Kong, Kiwoong Park, Harshit Goka. Let's give them a round of applause. And they were anticipating being here, but unfortunately could not at the last minute. This one will be tomorrow night. Okay, there's going to be three oral sessions each day, one at 2:30, one at 3:45, and one after dinner at 7:30, right before the poster session. Okay, so this will be tomorrow evening. And this one will be presented in one of the remote sessions. Last but not least, best paper for applications track. Character GAN, Few Shot Key Point Character Animation and Reposing by Tobias Hintz, Matthew Fisher, Oliver Wong, Eli Schechtman, and Stefan Wormter. Sorry. Let's give them a round of applause. I think actually Tobias is the one that's going to be presenting. I may have made a mistake there, but I'll double check that after. Again, this is going to be the first session on Friday. Okay. So last, we are very close to having a location for next year's WACV. And the picture may be representative of where it will be held, but we're gonna provide an announcement for that very soon. So stay tuned. We do have a team already largely assembled. I'll be involved with a great set of program chairs. Richard, my program chair, co-chair this year, and several new program chairs will be leading the program chair committee. So I'd just like again to thank all of those that have been involved in organizing it, everybody who's here attending. Thank you so much. Let's give all the organizers and everybody here a round of applause. Okay, so we're gonna switch real quick to Zoom for our first talk. Matthew, are you there?
Hello, yes, I'm here. Hopefully you can hear me.
Disconnect this or?
No. Let's go under sounds again. Have Matthew try again. Matthew, say something.
Are you able to hear me? I guess not.
Matthew, can you try the audio again?
Any look now?
Matthew, can you try the audio?
Any look?
So you're not in host mode. You need to share your sound. Can you actually log into Zoom with the account I give you? Instead of going through this link? Matthew, it's going to take a second. We have to log back out and back in. Zoom dash 36. Advanced. That UCCS.
Okay, Matthew, can you try?
Yeah. Are you able to hear me now?
No. Is that coming out of the? No.
Matthew, try one more time.
How about now?
Oh, it's actually coming out of the laptop. No. Try again.
Is it any better now?
No.
Yeah. Matthew, can you say something?
Something. Are you able to hear me?
Okay, Matthew, can you say something?
I can try.
Yes.
Is it working now? Is that me good to start? Yep,
Go ahead, Matthew.
brilliant. Well, I'll just start with a quick thank you to everybody involved in organising the conference. I can imagine it must have been a lot of work in these times. So thank you for everyone involved in getting the conference up and running. I'll get straight to presenting the paper, which is Agree to Disagree when Deep Learning Models with Identical Architectures Produce Distinct Explanations. I'm Matthew Watson, and this was joint work with Bashar Hassan and Noor Al-Mubayed at the Department of Computer Science in Durham University. And we were sponsored by ERDF and CEVA Limited. So recently there's been a lot of work put into the field of explainable machine learning. So we want to produce techniques which can explain the decisions behind machine learning models, try and open up the black box. And there's been many proposed methods to provide explainability, with some of the most popular ones currently being post hoc methods. And these are popular mainly because they're typically adaptable to most deep learning architectures, and they provide local per sample explanations, with the current de facto post hoc method being SHAP. And SHAP, to give a brief explanation of how it works, if you're not familiar, it models the problem as a game, with each feature in the input being a player in that game, and then uses Shapley values to calculate attribution values based on how much the model's output changes when that feature is removed. So on this slide, we have a couple of examples using SHAP. So in the top right, we have an MNIST example. And along the bottom here, we have chest X-ray samples from the Mimic CXR dataset. So on the left, we have the original sample. Here, we have the SHAP values from a DenseNet 121 model trained with random seed 2. Here, it's the same DenseNet architecture, but trained with a random seed of 5. And this is the difference between these two SHAP values. And you can see that the difference is quite significant. And it's these differences that this paper investigates. So where can variations in models come from when we're keeping the model architecture identical? Well, it comes from training hyperparameter choice. So if you change the random seed, the dropout, the order of the training data when training the model, you'll get a slightly different final model at the end. And what we want to do in this paper is explore how model explanations change on identical architectures when these training hyperparameters are changed. So to first do this, we need to come up with some sort of measure of explanation inconsistency, which is what these two equations show. So this first one is essentially just a normalized version of separability. So what we do is we train multiple versions of the same architecture, each with a different training hyperparameter changed. And then for every pair of these models, A and B, we calculate the separability of the explainability values. And this obviously raises the question of, well, how do you measure separability of the explanation values? And in the paper, we look at multiple possible approaches to this, including information theoretic measures such as Jensen-Shannon divergence, statistical tests such as a few hypothesis tests. But in the end, what we settle on is simply using the accuracy from a binary logistic regression classifier. And this is essentially just due to its ease of use and its applicability to pretty much any scenario. And this is what the bottom equation is showing. So this is our measure of explanation inconsistency for some given model architecture. So essentially what we do is we train binary logistic regression classifiers on the SHAP values from two identical deep learning models, where the two deep learning models were trained with different hyperparameters but crucially they have the exact same architecture. And we do this multiple times for every architecture we test. And these two plots on the right show our results. So this top one shows the separability of the SHAP values across each of the model architectures tested on both the MNIST and the MIMIC CXR datasets. And as you can see, across both datasets and every single deep learning model architecture tested, the separability of the SHAP values is extremely high, showing that there's quite a large difference between the SHAP values produced by a model trained with hyperparameter A and a model trained with hyperparameter B. This isn't the case for SVMs, showing that this is most likely an issue with deep learning models and not kernel-based models. This bottom plot, this scatter plot, is of explanation consistency versus explanation quality metrics. In this case, to measure explanation quality, we use infidelity and sensitivity. And as you can see, there's very little to no correlation between explanation consistency and quality. And this essentially shows that the issue most likely isn't with the explanation techniques themselves, and is instead with either the model architectures or some inherent issue with deep learning. So this is our full set of final results. You can see every model architecture tested on the two vision data sets tested, so MNIST and MIMIC CXR chest X-ray data set. And you can see that across all of the architectures, across both data sets, and across both explanation techniques tested, so this lot is SHAP, these bottom three rows are for integrated gradients. Explanation consistency is extremely low across the board. And this is despite the accuracy of these models being at or close to state of the art for the relevant tasks. And note that the accuracy of these models changes nowhere near as much as the explanations have been shown to change. It's perhaps also worth pointing out on this slide that clearly explanations produced by integrated gradients are a lot less consistent than those produced by SHAP. This is likely due to the fact that integrated gradients is obviously a gradient-based attribution method and is so more susceptible to small changes in the network. So to conclude, we've shown that models produce significantly different explanations when hyperparameters are changed. And this obviously presents significant barriers to deep learning adoption in sensitive scenarios. You can think, for example, a doctor, which might be looking at using the machine learning models for disease classification or something, will be a lot less likely to trust a model where explanations can be shown to be this inconsistent. And we hypothesize that our results probably show that models likely aren't learning causal features, because if there were learning causal features, we would expect the models to learn the same causal features every time it's run. And so the explanations would be more consistent. So in the future, what we want to do is develop model architectures that can produce more consistent explanations, if this is possible. And then we want to, of course, extend our work to different data modalities. So in this study, we focused purely on image data, but is it also present in text data or time series data, for example? And that's about it from me. Does anybody have any questions?
Hi.
Hello.
Yeah. So I had a question. So this difference in explanation for models with slightly different parameter but same architecture, has it been observed across different kinds of model architectures, like for transformers, ResNets, or
Yeah.
like maybe token mixers? So it has been observed across everything, right?
So everything we've tested has shown this problem. So everything from simple MLPs to small CNNs to ResNet, even to ensembles, which we'd possibly expect ensembles maybe not to show as much of this problem, but we found that it's still present. So everything
What
we've tested in so
Okay,
far
so
is showing the
like,
problem.
like, do you expect the same thing to happen even with attention mechanisms like transformers? Because like that captures this relationship between pixels into a much larger, like it's a non-local mechanism, right?
Yeah. So that is sort of leading on to the future work we want to look into. But
Okay.
my intuition would say it probably still would occur, but maybe not to as much of a degree as it's in, for example, a simple MLP. But we haven't tested that yet.
Yeah, because in transformers the attention maps usually point to, like, it shows that like the localization is mostly correct, but yeah, it would be very interesting to see whether like same architecture but like what are exactly happening, because like we just look at the attention maps and just leave it at that. We don't dig deeper into the interpretability.
Yeah, definitely. It'll be extremely interesting to look at.
Yeah, thank you.
Great, thank you so much. In the interest of time, we're going to move on to the next talk, but thank you, Matthew, for your presentation.
Thank you.
Sorry about that. Yeah, video textures uses Euclidean pixel distance as the similarity metric between frames. This makes it brittle to videos with, sorry. Okay, this makes it brittle to videos which contain irregularities and chaotic movements, such as dances or musical instruments. So here's a video of, again, a person playing guitar, and this is given as input to video textures. And so here's the result. As you can see, the synthesized video is very choppy, and it contains many poor transitions. So the red bar that you see at the bottom shows part of the input that's being played. So as the first solution, we try to use state-of-the-art GAN-based video generation methods to do this, but they failed pretty badly. So we fed these two videos of a candle flame and a guitar to MocoGAN, which is state-of-the-art GAN-based video generation method. And here's the output. As you can see, it contains a lot of artifacts, and the videos don't match the realism or the temporal dynamics of the input videos. So to solve this problem, what we did was to exemplify graph-based sequence generation methods with contrastive learning techniques. So we introduced contrastive video textures, which is the learning-based non-parametric method for video synthesis. Our method learns feature representations and a distance metric to compare frames, and produces a smooth video with seamless transitions. Here's an overview of our approach. At a high level, we train a Markov model that learns to predict the next frame given a current frame. So given any input video, we first extract overlapping segments from it. Next, we learn feature representations and a distance metric for these segments by fitting a bigram model. So given a query segment VI, we learn a representation that is similar to the positive segment I+1 and dissimilar to the randomly sampled negative segments, which are sampled from the rest of the video. Additionally, this model is trained in a self-supervised fashion using contrastive loss. To synthesize the video during inference, we start with a random segment and use this fitted bigram model to compute the edge weights and the transition probabilities to the remaining segments in the video. Since we want our textures to be variant, we scale the temperature term to modulate the sharpness of the softmax distribution. And so this gives us many positive weighted edges, which we denote in green, and negative edges, which are denoted in red. And the thickness of an edge corresponds to the probability of transition. We randomly traverse along one of the higher weighted edges to reach a second segment. Next, these two segments are appended to the output, and the process is repeated with the second segment as the query segment. To allow for large changes in motion, we also include interpolation. Now, to synthesize a video condition and an audio signal, we do something similar. We divide the input into video and audio segments. We use the fitted bigram model to compute the video transition probability matrix. And then we divide the conditioning audio into segments of the same size. Next, we compute the similarity between the conditioning audio segment and the input audio segments. Using this, we get the audio transition probability matrix. The two matrices are then combined using a weighted average to come up with the final transition probability matrix. And the video is synthesized using the same inference procedure, which I just described. So moving on to some results and comparisons to baselines. So first, the unconditional setting where we don't use any audio. So here's an input video without any audio. And here are the results from the classic method and its variants. So as you can see here, the results which are produced are pretty choppy. The methods all loop over the very first few frames in the video, and they appear to be stuck. Next, we changed the raw pixel features which are used in the classic method to ResNet features, and we trained this classic deep baseline. While this result is more diverse, it's definitely not smooth because the model picks a lot of poor transitions. And finally, here's the result from our method. So as you can see, the result produced by the contrasting model is very smooth and it has seamless transitions. The red bar, which transitions to new positions, shows that our textures are dynamic and diverse. And here are some results from the audio conditioned video synthesis. We first compared to visual rhythm and beat. It's a baseline that warps the video to match the beats of the conditioning audio. So as you can see here, it essentially played the title frame. And that's because this method wasn't designed to select the right frames that align best with the audio. Random replay is a baseline where we overlay the conditioning audio on a random section of the input video. So again, the problem with this was the audio and video are misaligned in certain instances. Sorry, I just can't see it. Okay. All right. So. Okay, audio nearest neighbor was a baseline where we took the conditioning audio and found the nearest neighbors in the input target audio and picked the videos that matched it. And again, over here, the input, the video and the audio were not aligned all the time. In Classic plus audio, we added audio conditioning to the classic video textures method. So here again, the output is not smooth, and because classic video textures isn't able to handle audio conditioning. And finally, here's the result from our method. Okay, as you can see, the audio and video were best aligned in our result, and our method was able to identify gaps in the input audio, in the conditioning audio, identify a change of pace, and also produce a semantically meaningful output. So in conclusion, we revisited this classic non-parametric video synthesis method for infinite video generation from a single input video. We saw that GAN-based video generation methods fail pretty badly in this setting. And a simple fix for this L2 distance was to replace it with the by learning a visual similarity metric. And this also enables audio conditioning. And we could see that the resulting videos in our case were more diverse and also temporally coherent. And here are some more results. Thank you. Any questions?
Yeah, I'm curious, what's the fidelity between videos and
Oh, that's a good question. I guess the way we evaluated this was through user studies, but whether you can like learn to play a new song watching them, yeah, not quite sure. We didn't really like actually evaluate if the chords were matching, and that is something I think is a good direction for future work. But yeah, that could be pretty cool. But right now we haven't evaluated that. Yeah. Yeah.
One more from the audience here.
Mhm. Yeah, exactly. So I guess oh, sure. Yeah, I'm just going to repeat the question. It was basically if the cards were matching in the synthesized videos when we conditioned them in an audio. And yeah, that is something we didn't evaluate. We only evaluated for like the realism of the output, whether a novice player or someone, yeah, who hasn't really been trained to play the guitar can tell if it's like a synthesized video or not. And also compared to like the baselines, we were able to fool people more often. And but we didn't really evaluate if the chords matched, and we didn't really have that ground truth data to train our model with either. Yeah.
Any last questions? Excellent.
Thank
Thank
you.
you. Thank you again. She'll be available during the poster session tonight. Okay? Unfortunately, the only one who's on site, but she'll be available tonight. So our next.
Hello. Hi, can you hear us? Can you hear me? Can you hear me? Please answer on the chat. Thank you. We are the authors for the whole robust wireframe detection method. Thank you so much for the award, and I am Nejin Kong. So let us talk about.
Can you start over?
Okay. Hello. Hello. So let me start the presentation then. So thank you so much for the award. We are the authors of a whole robust wireframe detection paper, and we three are all available in a conference room in Seoul here. And thank you so much for the award again. And I am Nejin Kong, and let me talk about this method. Here we see a typical example of an indoor scene about the man-made structural environment surrounding us. Wireframe is a line segment-based representation designed to well capture large-scale visual properties of regular and structural shaped man-made scenes surrounding us. However, we often face that the underlying scene is occluded by a foreground object that may be too large to ignore easily. Unlike wireframe, conventional edge or line segment detection methods focus on all visible edges and lines, producing spurious results not well aligned with the salient structure of the scene. And existing wireframe detection methods are not really designed to predict hidden structures behind the larger occlusion. On the other hand, our approach knows how to predict the wireframes well aligned with the salient structure of the scene across the large occlusion as you can see on screen. So let us talk about how to estimate the wireframe robustly to the whole occlusion. First, let's talk about a popular basic framework for wireframe detection without hole. Its backbone network predicts the junction and line map first, and they are converted to coordinates and matched to get line segment proposals. And each proposal is verified to obtain final line segments with scores assigned. However, these existing models are yet unable to handle large Hall occlusion. In order to solve this problem, we propose three novel ideas on top of the basic framework. that makes the framework far robust to large Hall occlusion and even improves the performance without Hall meaningfully. So let me talk about each of the modules of our approach. First, we introduce a new conditional data generation method and training techniques to let the model understand the holes. We transform the traditional training data with wireframe labels into a conditional data by superimposing a foreground silhouette on top of the image and also introducing a paired binary mask map with the hole to make the data to be conditional. And when we create the data, we found that by carefully controlling the size, which means progressively increasing the hole size during the training, was more effective to improve the conditional learning performance. And also by controlling the placement of the hole while avoiding the isolated components, we're also more effective in randomly placing the holes. Second, we also introduced so-called RGB GAN, where the GAN stands for Generative Adversarial Network, to encourage the model to better predict the underlying hidden structure of the scene, even beyond the hole. In order to make the basic backbone network into a generator, we introduced a decoder and a discriminator, and by combining these, the basic backbone network now turns to a RGB generator, where the hidden area behind the hole is filled in, as you can see in this photo. And in order to train this GAN network, we introduced the new GAN losses, as you can see in this slide, which are composed of 4 losses. They all help together to make the RGB GAN generation perceptually and visually more realistic, as you can see in these photos. Please note that the generation results are only for the visualization and used only for training. During the testing time, we don't really need the decoder network for the RGB generation. And third, we introduced the semi-supervised learning called pseudo-labeling here. We create a large-scale pseudo-label data set to overcome a lack of ground truth images, the short of ground truth images. So in order to do that, we first collect a large-scale pseudo-labels and filter them out, which are less accurate or less densely annotated based on our statistical heuristic. And finally, as you can see in this screen, the obtained pseudo labels look a lot like ground truth labels with fine quality. And in the training steps, we first enlarge the model capacity by taking this large scale pseudo data and then enhance the fine level accuracy by fine tuning the model on the ground truth wireframe training set with all. Finally, we obtained fine results, as you can see on screen. Unlike the state-of-the-art existing works, our work can estimate the wireframe robustly across the whole without being distracted by the larger occlusion. And as you can see in this image, existing methods may leave an empty area where the hole is, or mistakenly detect false line segments around the hole boundaries, while ours can predict the wireframes robustly regardless of logical occlusion. And we also found that our work can improve the performance of ordinary wide-range detection without hole. As you can see, our results are comparable to the results from the existing models. And we also applied our model to the real-world examples where the true occlusion exists. So when we found what we found that the existing works may confuse with the significant foreground objects, as you can see on the left, while when we provided the mask maps detected automatically by applying panoptic segmentation, the wireframe estimation by applying our approach works far more robustly compared to the existing works. Let us show some of our analysis to support our claim. We took a standard wireframe test set and we tested it with or without hole. And as you can see, compared to the state-of-the-art works, our approach applied to the HT/HKWP framework performed the best, as you can see in the table. And the PR curves derived from the previous the experiments in the table even more clearly proves our claim, where the red curves red curves are respect to our full approach, and without hole and with hole, it all performed clearly better than the existing work that we have compared. Let us show some calculation study to show the effect of our approach composed of 3 modules. By applying the first and second modules, which stands for which corresponds to the experiment B, and also the green curve in the peer curve graph, it already dramatically outperformed the existing work. And by applying the pseudo labeling, it even further improved the performance as shown in the red curve and the red text in the table as well. And these also were consistent with the case without hole, which improved the performance without hole meaningfully as well. So in conclusion, we propose a novel approach to detect wireframes in a whole robust manner for the first time in the field. And our approach is highly robust to hole occlusion, unlike existing works, which even improves the ordinary detection without hole meaningfully. And as written in the paper, we found that our approach can be flexibly applicable to most recent basic frameworks if they share a similar backbone architecture. And in the future work, we would like to extend the approach to different types of backbone architectures. And we also would like to explore global attention to enable even deeper and broader understanding in the model. So thank you. So this concludes our talk. And if you have any questions, we are happy to answer. Hello there.
Can you hear us on Zoom? Are there any questions on Zoom? Okay. Well, thank you, Najin, for your talk. Very interesting work.
Okay, thank you.
Excellent. One thing I want to remind everyone, both for these award talks and all of the talks, all of the papers, if you want to interact with the authors on the virtual platform, you can post messages. We're going to have throughout the conference 4 parallel sessions, at least 2 of which will be asynchronous. And the only way to interact with those authors is on the virtual platform. Okay. So thank you, Najin. Again, that was the best paper for algorithms. Let's give Najin a round of applause and his co-authors. So our final talk for this award session will be by Tobias Hintz. He and his co-authors, Matthew Fisher, Oliver Wong, Eli Schechtman, and Stefan Bermter are for the best application paper, character GAN, few shot, key point, character animation, reposing. So Tobias, you're there?
Yep. Can you hear me?
Yep.
Yeah, perfect. Okay, then, yeah, thanks everyone for being here and for inviting me. We just want to say thank you to for the award and everything. Yeah, so this is joint work between the University of Hamburg and Adobe Research. I'm Tobias, and my co-workers are Matthew Fisher, Oliver Wang, Eli Schechtman, and Stefan Bermter. And basically, our key problem is to animate 2D characters. So it can be animals, can be humans, anything else. And usually the main challenge here is that this is a lot of work. So you need like professionals that will sit down and draw intermediate frames to get this to work, which takes a lot of time and is pretty expensive. What we have though on the internet especially is we have a lot of different characters available. So these might be sprite sheets, these might be manual drawings, artistic drawings, drawings by kids, whatever we have. The problem here is we only have a few examples, right? If you draw a couple of images, it's fine to draw maybe 5 or 10 images. But if you have to draw 100, that's a lot of work and you don't really want to do that. So of course, people have looked into this previously. How can we make something work if we only have, let's say, 10 images? And there are a couple of ways how you can address this. So of course, the first sort of straightforward approach is just draw everything you need. Like I said, that's a lot of work. Another thing is just to use typical video frame interpolation approaches, which tends to work fairly well. But again, the main limitation is that you do still need a decent number of frames to start with. So if you only have 10 frames to start with, you can't really do that much with interpolation methods. Another approach that is a little bit more smart sort of is that you can warp the individual images based on some warping points that you manually define. This works relatively well. The problem is that, as you can see, for example, here in the animation, with moving characters, you have occlusions and disocclusions. So body parts may move in front of other body parts. They may reappear at different locations and so on. And this is pretty difficult to handle with just warping points. So basically our approach is to address this with a generative model where we just define a set of key points and layers for our 10 images or however many we have. We train our model and then we can do some animation and reposing. So the approach is actually fairly straightforward, I would say. So given some images that we have, 2D RGB images, we label them. So I don't know how well you can see that on the slide here, but basically we just manually define some key points on semantically meaningful body parts. So this is done manually, but you could also use a pre-trained network if you have one. And the key novelty here is that we also define layers. So in our case, we always have 3 layers, roughly translating to sort of front, middle, and back. Basically, from the camera perspective, which body parts are closest to the camera, which ones are like in the middle, and which ones are in the back. And I'll show some examples for that later. And that's all we need. And then we train our model, and now we can use that model with the given key points, and we can use animation or reposing by just moving around the key points between different frames. And this is what our model looks like. So basically, like I said, we split our data into different layers. So here's an example of what this may look like for a human character. So you see the top image is basically the, in this case, the front part. So that would be the right arm and the right leg. And those are the key points for the right arm and right leg here. Then the middle part is sort of the middle part in this case, which would be the torso and the head. And the bottom key points you see here are for the back part in that case, which would be the left arm and the left leg. And all those key points are handled by different parts of the model. So we have one model or different layers for the different convolutional layers for the different key point layers. And once we have created features for each body part, we concatenate them and we merge them. And the merging is sort of similar to what Spade does. So basically, we just scale each feature. And maybe the intuition behind this is that, for example, if the left arm is not visible because it's behind the torso, then in this case, we could zero out those features because they're not needed because they're not visible. Whereas, for example, the right arm is always at the front for this character, so we would never zero it out. And here are some results of what we can achieve with this method. And you can see how many training images we used. And I think throughout the paper, for all the examples that we show, we always use between 8 and 15 training images. And that's something that you can typically find on like sprite sheets that you download from the internet. And again, we don't have any specific requirements. You just need RGB pixel data. So you don't need vector graphics or puppets or meshes or skeletons or anything like that. So those are a couple of two-legged characters. We can also do this for animals with 4 legs, or like in the ostrich case, an animal with 2 legs. And you can see like we get pretty smooth movements, and they also are reasonably synchronous, and we don't really get any big artifacts or anything like that. So here's maybe a better example of the benefit that we get with layers. So here we have 4 individual characters where you see the output of our model with some zoomed in. So for example, for the dog here, you can see the legs, for this ape here, the hands moving in front of the head. The dinosaur, we also have the hand and the foot, same for the fox here. And you can see this looks reasonably realistic. And the interesting part is what happens if we don't use the layers. So basically using just the traditional approach of feeding the key points to the generative model directly. And this is what we get. So you can see, for example, if we look at the dog, there's like, you can't really see which parts belong to the individual legs anymore. You see here for the ape, if it moves the hand in front of the head, it doesn't look realistic at all anymore. We just get some weird artifacts and features. Also, if you look, for example, at the fox or the dinosaur here, you just see there's a lot of, essentially artifacts, because it's pretty difficult for the model to figure out which body part should be in the front or which body part should be visible and which body part should not be visible. Because remember, we only have like 10 images or something like that. So for the model to figure out from only 10 images, which model part or which body part should be visible at different times is pretty difficult, because we may only have 1 or 2 examples for each sort of roughly each pose. So by introducing those layers, we basically instill this implicit bias into the model that different parts are differently important, and that different parts are maybe in the front and will always be visible, whereas other parts will not always be visible. And we can see that this has a pretty drastic effect most of the time. And also we do some quantitative evaluation on held out test images. And also there we see quite big improvements across the board. And the only thing we sacrifice for that is, of course, we need some human information about the layering of different characters. Then again, like I said, we really only use 3 layers for all our test cases. And it always works. But of course, if you have some very specific characters or some very specific camera angles or something like that, maybe you need to define some more layers. So that's something that we still need to define manually. But aside from that, it's pretty straightforward labeling those images, because we only have to label 10 images. So you can do that in 2 or 3 minutes. Then you train the model, and then you can really do either interactive reposing by just dragging around key points, or you can also do the animations that I showed here by just basically interpolating the key points positions between different images and then generating conditions on those key points. Of course, you can also use this on real persons. So we took a YouTube video here of a person walking. You can see the training data here. We just extracted some random images or some random frames. And here we can also compare to other models that already use this. So we have some 2 state-of-the-art models that were trained on the fashion data sets. So they fail completely here, because the fashion data sets doesn't really contain any walking people. It's people posing frontal to the camera. This model here is also released recently, works relatively well, but this model is already fine-tuned on the training data. So this is a model that is pre-trained on a large data set, and then you need like 1 or 2 minutes of fine-tuning on your specific use case. So that's why it works reasonably well. And finally, our model that is only trained on those 15 images that we took randomly. And again, you see it really performs a lot better. So I think maybe one of the big advantages that this model has is that you can really model a lot of edge cases. So imagine, for example, humans wearing very specific clothing, very specific hats or dresses or something like that, that you wouldn't see in traditional data sets. And then those models that are trained on those traditional big data sets, they will fail to model this, like specific movements, specific clothing, anything sort of out of the ordinary. Whereas our model is fairly well versed to model those images because we just train it for that specific use case. So it may not be like widely applicable to other images or to other persons that we see later, but really for specific use cases, it works fairly well. And again, you only need like 10 to 15 images to make this work. Yeah, so this was it from me. We have the code available if you want to check it out. Otherwise, I'm happy to answer any questions now, or you can also ping me through the WACV system. I see a question in the chat. Just let me read it quickly.
So I'll read the question for the audience here. It sounded like the input was a few, for example, 10 3-layered images. Your tool's advantage over morphing was occlusion, but does it do more occlusion one could manage by morphing those 3 images individually? For example, what if I had a spinning ball that locally has 4 mid and background, but those elements change categories over time?
Yeah, so that is correct. You can do the morphing if you take those images individually. The challenge, I would say, is that, I mean, essentially then it's fairly similar to what we're doing, except that you still have to do it manually. Whereas in our case, obviously, because we train the model, it does it automatically. The advantage is that we do sort of define those layers, but we never actually define which pixel belongs to which layers, right? We only define those layers for the key points. So for example, the model learns that the area between, let's say, the hand and the shoulder is one continuous area, namely the arm, and belongs to a specific layer. So we never tell our model that the whole arm belongs to a specific layer. We only say the hand and the shoulder belongs to a specific layer. So basically, we don't have pixel-wise annotation because that would be pretty expensive. We only have the very sparse key point annotation. And if you want to do straightforward morphing, you still need some form of understanding which layers each pixel, I guess, belongs to a degree, which may be a little bit more expensive or difficult to obtain. Whereas our model learns this from the few training images that we have.
Great, and thank you, Sam, for that question. Anyone in the live audience here have a question for Tobias?
There's another question in the chat, if you want to read it out.
Ali, do you want to ask it yourself or you want me to read it?
Sure, it's a very good work. I'm just wondering if there is any quantitative or qualitative studies to demonstrate how the model's performance improves if additional training data is available. And I understand that right now, the model actually performs greatly with a few samples. So I'm just wondering if that has been done.
Yeah, so we did, in fact, for 2 characters, we had more training images, sort of. So I think for 2 characters, we had around 100 images, and we trained the model on the 100 images for each character. It performs a lot better. So it seems that, like with most cases in generative models, more data is still better. I guess it's to a degree a point of diminishing returns, because once you have hundreds or maybe even thousands of images, I think frame interpolation or more traditional interpolation approaches also tend to work fairly well. So at some point you'll have to have this trade-off, because remember, at least in the current setting, we still have to label key points. So since we apply this for specific use cases, I tried to use some like pre-trained models to label key points for those characters, and they fail completely. So the problem is, if you have 100 images, our method will work perfectly fine on that. But if you don't have a pre-trained model to label those key points, you'll first have to label 100 images with key points. And again, if you have enough data, traditional interpolation methods may work just as well. But our model does work with more data. That's not a problem. And I think Sam had one follow-up question.
Yes. Sam had asked, you only select certain points as for, middle, and back. How many points do you tend to click per image?
Yeah, exactly. So basically, we don't have this pixel level annotation. We really have the sparse key point annotation, which we then assign to layers. I would say on average, we had between, I'd say 10 to 12, 10 to 14 key points per image. So basically, usually what so I didn't do a lot of studies on that, and it just tended to work reasonably well by just labeling key points at semantic areas that would make sense for me. So for example, for a human, that would be hand, elbow, arm, head, torso, foot, and knee, roughly. Basically, the joints that move. Anything that is connected to those joints is then learned by the data. So I would say, I think usually 10 to 14 key points. And it's relatively straightforward. So I think to label 10 images with those 10 to 14 key points for me took maybe, I don't know, 3 minutes, plus minus. Depends on what kinds of tools you have, but it's pretty fast.
Great, thank you, Tobias. Let's give Tobias one more round of applause. Thank you so much. So that concludes our award session. Again, congratulations to all 4 papers. A couple quick things. First, I want to thank Terry Bolt for his help with the AV, and also Ginger as well. They're going to be in this room for the A sessions, and Ginger will be in the other room for the B sessions, making sure that everything goes smoothly with the videos. So thank you to Terry and Ginger. I also want to thank all of you both here in person and on Zoom for it's a little difficult to do a hybrid session. We're hoping that the other sessions should go relatively easily, that they're either going to be remote or live, not hybrid like this. But thank you for your patience. Really quickly, this room is now PACA 1, 2, and 3. So all of the A sessions and the keynotes will be in here, okay? On the opposite side of this, sort of directly behind us, is where the B sessions will be, and now PACA 5, 6, and 7. The poster sessions tonight will be in the middle stretch right here between these 2 A and B rooms, okay? So we're gonna have about a 5-minute break, and then the sort of 1A session will start, okay? 1A here, 1B on the opposite side. There'll also be 2 asynchronous sessions with papers for the authors that could not be here. Those are gonna be in the Paniolo rooms, which are sort of to my left over here, your right, okay? Feel free to come up if you have any questions, but thank you for being here, and let's thank the authors one last time.